Hi, everyone. I'm glad to see that so many are curious about microcontrollers. I believe it's the only talk on this subject or anywhere close at this conference, so it's very good to see a full room. I have with me, before I start the presentation, a bunch of MicroPython compatible devices, as much as I could find around home, maybe 10 or so. So afterwards, I am planning to go downstairs to outside the tutorial area, and anyone who wants to play with some MicroPython is welcome to join, related to machine learning or not. You only have 10, so you have to play nicely together, maybe, if there's many interested. So, I'm the head of data science at Soundsensing. We're a provider of predictive maintenance solution for ventilation systems in buildings. So we work a lot with sensor data, and we use Python as much as we can for data science, IoT, and backend tasks. And the goal of today's presentation is that you, as a Python developer with some experience with standard Python machine learning libraries, such as scikit-learn or Keras, is able to deploy a machine learning model to a microcontroller device, even though you maybe never done anything like it before, using emlearn library and MicroPython. So as a quick outline, we'll cover very briefly just some background so we know that we're talking about the same thing. And then I'll give super brief introduction to MicroPython, which is a Python implementation for microcontrollers. And then cover more in depth the emlearn TinyML project, and then how to use emlearn with MicroPython in a practical example setting. So what is a microcontroller? Well, it's a tiny programmable chip, and although you might not see them much, they are basically all around us. So any electronics device that you have in your home will have, if it's from the last 20 years or so, will have one microcontrollers or two or three or so inside that is controlling that unit. And a modern car, for example, has over 50 microcontrollers as working in a combined system. And there are over 20 billion microcontrollers shipped every year. So that's more than, 5 times the population of the world every single year. So this stuff is like dust. It gets everywhere. But it's mostly used then in like very industrial settings, but it's increasingly more and more accessible for hobbyists. So there was this Arduino project started in 2010, which really made some big steps in making it easier to access at a lower cost and like friendly documentation, no signing of NDAs or like all that kind of industry standard bullshit. And then in 2014, there was the MicroPython project was started and first release. So that's when we could start to use MicroPython on such devices. And then going to 2019, we got much better hardware. It improves all the time. So you can have MicroPython-based devices that no longer feel like so constrained. You'll have a lot of RAM, which by my microcontroller standards is like several megabytes. It's not just kilobytes, it's megabytes of RAM, imagine that. And you have devices that maybe like around the power of the original Pentium 1 devices, which you can do a lot with. Anyone has worked with Amiga in the way past, that's basically, we are now above that. You can get Amiga grade device for under $1. So yeah, it's all around us. And when it comes to machine learning on microcontrollers, we're obviously not going to be running any large language models or generative image models or anything like that. But one use case where machine learning is incredibly useful is in analyzing sensor data. So sensor data has gotten very, very good and very cheap as well the last years, mostly driven by smartphone development, microphone, accelerometers, all kind of stuff, cameras. But then to get some interesting information that you want to act on, for example, out of these in an automated way, you often need to use machine learning to analyze this raw data. And if you do this all on the device, it's a bit trickier than just sending it to the cloud and using your existing, all your existing tools that you're familiar with. But you get some good benefits. The system can work 100% standalone without any network connectivity, can have a low latency. For example, if you're supposed to react to something, do something in the physical world with this understanding that you've gotten through the ML. You can also make highly power efficient systems that can run on battery for years. And you can preserve privacy by not transferring the raw and potentially sensitive sensor data. Instead, just extracting what is interesting and not privacy sensitive and transmitting that. And they can be very low cost, which makes then possible to have really large scale. For example, to put a sensor on every single pump. So there are many applications of machine learning microcontrollers. Some are already quite standard. So when you say, hey, Google, or Alexa, or Siri, and so on, that listening for that phrase specifically is usually done by a low-power microcontroller. And then once that phrase is triggered and recognized by machine learning, it will then hand over and buffer the data and send it to the cloud for the full speech recognition, which does not happen on the microcontroller. And sleep tracking, for example, is another standard application, or activity tracking in general. Also activity tracking for cattle and livestock. That's an application that has been done with this library. Because you can detect whether they might be sick or there are some stressors that are influencing them. And then we work at Soundsensing a lot with pumps and make sure that their health is good. And then there's also a lot of just hacker fun projects. For example, don't you want a cat door that will automatically open for your cat and not any other cat, but only if it doesn't have a mouse or a snake or something like that in its mouth? So this is something that someone has really built. And down here is a magic wand, so you can make a gesture like there it's from Harry Potter, and then to trigger whatever you want, like turn off the lights or turn on. So there's applications everywhere, and it's getting more and more common and fun to play with. So emlearn is a machine learning library, open source library for implementing such systems. Basically, a scikit-learn for embedded systems. And two key features is that you have convenient training, so you use just your standard scikit-learn Keras tools, so you don't need to learn anything new there. And then as time progresses, they improve, and you get all these improvements in these projects too. Then you have an easy way to export that into a C model, and this is the core library, and we're going to work on the MicroPython bindings a bit later. And then the C code itself is embedded friendly, so you could use it in a professional project, has test coverage. It supports the tiniest microcontrollers as well. Yeah, so that's the core. And supports the most common tasks for embedded or even standard machine learning. You want to do classification usually, maybe some regression, and maybe some anomaly detection. And it supports a set of models, not everything that you have in scikit-learn with some, but the subset that implemented and that are useful for these kind of devices, which still are constrained on memory and compute. So tree-based models are very efficient. K-nearest neighbor is very useful. You can also do on-device learning with that. And Gaussian mixture models and simple neural networks we support. So the library has been around for around 6 years now. Started by me, and it's been maintained by me since that time, with a couple of contributors here and there. And I'm aware at least 30 R&D projects or industrial projects that have published papers that have used this library. And there's probably things that they don't know either. It's typical for open source, including some stuff from research from Samsung and this cow tracking research from Virginia Tech and from Sandy National Labs about monitoring large electrical grids. So, but the part that's most interesting here is that we quite recently, like last year in August, started to make MicroPython bindings. So in the same way that you use probably NumPy, Pandas, TensorFlow, all these libraries all day, they're implemented usually in C++ or maybe in C. But then they have Python bindings, which makes all that power available to you in a very convenient manner. And that's the goal of the MicroPython bindings for emlearn on these small kind of devices. So yes, to balance that convenience and productivity with the speed of C. So there's just I haven't done a lot of benchmarks, but here's a small benchmark to some pure Python implementations of random forest that they generate a small piece of Python code, or it gets quite large, usually the trees. And emlearn is around 100 times, or up to 100 times faster than that, while still having it's very easy to install. It doesn't require much more tooling. And this is possible because MicroPython has a nice feature where you can install these native C packages at runtime, which is quite unique, I think, in this high level for microcontrollers. I haven't seen it anywhere else. So it's an early development phase, and we're planning also to add some multi-layer perceptual and convolutional neural networks. Yeah, so quickly on MicroPython. Anyone here is familiar with this project? Either played with it or heard about it? Yeah, there's a couple. That's cool. And then the rest we'll learn a little bit about now. So it implements a subset of Python 3, and for devices which have at least 16 kilobytes of RAM. And this used to be a lot. Nowadays you can get a couple of megabytes. Has support for at least 8 microcontroller families, so you can use a lot of different hardware. It tries to be as compatible as is possible with CPython. But there are, of course, constraints in terms of memory usage, in terms of how to efficiently implement even basic things like floating point operations and so on. And it's mostly to the level of Python 3.6, and it has support for some of the features that have been added after that. A little bit mixed. So there's like a documentation page on the MicroPython which says like some things that are implemented, some things are not planned, and some things are maybe coming, if someone helps to contribute maybe. But there is no CFFI or C module compatibility. So that means that the whole world of PyData, which is usually quite a lot of native libraries, such as in Pandas, NumPy, TensorFlow, and so on, they will not work and will never work. And they probably wouldn't work even if you would implement it, because if you have 1 megabyte of RAM, NumPy will just eat it very quickly, and you will not be able to do much useful work with it. So there's a different world, right? We're talking about 1,000 times or smaller than your even the cheapest laptop that you could get, or phone. But it's as compatible as it's possible. So small scripts that you have that are pure Python will mostly work, maybe with some minor modifications, but you will not have this huge set of libraries for data science. So emlearn provides some of that. It has a package manager, which is also really cool on a microcontroller. It did not used to be standard at all. And this package manager supports loading C modules at runtime. So you can get, even though it's implemented in C and there was a compilation process and so on, you can get the Python experience. You just MIP install it instead of pip install it on your device. And that's really what I want to have, this Python experience. I mean, if you're comfortable with doing C, you could already use emlearn as a C library. And you can still do that. But this is really to make it accessible on the Python level. So the world of hardware is huge. There's not a billion of different variations, but there are thousands of different devices. So if you are considering getting started with MicroPython, I would recommend you start with the ESP32 family of devices. There's everything from bare chips, don't start with that probably, and development boards for a few dollars. And then you have complete devices. Like here I have a watch that runs Python, which is super nice. And there's like this middle one has a camera and this peer detection, so you can do motion detection, and a little screen. And then there's this little USB stick, which I really like to just have in my backpack, because it's super easy to just plug it in and I'm testing on that environment on a real device without any plugs or something like that. It's also great to have as a sensor, just put it in one of your old USB chargers, and then you plug that into the wall and it has Wi-Fi, and you can and Bluetooth. So has a lot of connectivity, huge ecosystem. It's probably the most popular also for MicroPython, and also like Arduino tutorials. You find a lot of hobbyist stuff. And it's actually in the ESP EDF, which is under there, that the SDK from the vendor is actually also pretty good, which is not common for hardware that software is good. It's usually very bad. So yeah, you get complete devices for $20 to $50. Super good and powerful. How would you install MicroPython? You can download. You will usually download pre-built firmware, and there's like a generic one that supports most of these ESP32 devices. You have to install a tool, but that tool is on pip, so that's super nice. You kind of erase it, so you clear any old code that's lying around, and you write the flash image. And when you've done that, the device will restart, and it will appear as a USB serial port, which has a familiar Python REPL. And there you have modules to access the peripherals and everything that is accessible on the device. And then there's a tool called mpremote, which you can install on your host, which you usually use to trigger this REPL, but you can also then copy files, etc. There's also IDE support. So there's like a Tony, which is a super simple IDE, but it's very nice to just play with this stuff. Or you can set up VS Code, of course, to work with these kind of devices for a more professional environment. So how do you make a machine learning application with combining this? So as an example, this is like taken from an example by Edge Impulse. They have some data available, and so I downloaded that, and they can detect basic gestures such as this. It's called continuous gesture. You can differentiate between waving or this kind of snake motion or up and down. So they're very simple things, but it's good for an example. So you need some data. Now we downloaded some, so it's easy in this case. Although you usually want to do at least your validation and test data from your device, because there's, as always in data processes, there's small variations, and those variations can trigger or mess up your machine learning model. And then you install libraries, so we'll show that, and you train a random forest model on your computer using scikit-learn. You export the model with emlearn, and then you load the model in MicroPython and run. So we'll go to this quickly. So just as a tip for recording training now, we're not doing it here, but I have done it otherwise. There's multiple ways. You can transmit it to your computer, but then you have a wire, which can be problematic if you're doing, workout detection or so on. You don't want to be on a wire. You can transmit wirelessly because those things have Bluetooth and Wi-Fi, but it's also just convenient, at least for accelerometer data, where it's not so huge. You can just store it to the internal flash, and it's exposed as a file system. So it's super, you know how to do this already. So this is just some simple code to write CSV without a library and just write it to a file somewhere on the disk. And you can just timestamp it, for example. You have an RTC that tells you the real time. Because you have 8 megabytes of internal storage. So that's always available, super easy to just get started with recording training there. And how to install emlearn MicroPython, the emlearn package that you use on your host on your PC that you install with pip as usual, and then the MicroPython library, which will go onto the device, you download from the GitHub, and then you copy it. And those magical bolded things there, extensive in 6.2, that's like that has to do with the architecture that we're on, because this is compiled stuff, and which binary version it is, so it's attached to the MicroPython version. And you can, in the docs, it says like, oh, for this MicroPython version, use this, and for this ESP32, use this. And then you copy that to the file system using this mpremote. Ideally, this would just work with MIP install, as you would kind of expect. But right now, there's no the support for native or binary packages are not yet in this MIP repository. That will hopefully be there in the future, make it easy. So one thing that's maybe not familiar to you when you are doing this sensor data, accelerometer, for example, or sound, it's a continuous stream of data, and then your model needs a fixed length set of data. So how to get these worlds to combine? And the standard approach is that you take your stream of input data and you slice it into these windows. And you usually have a little bit of overlaps. Your model has like multiple chances to kind of catch the same phenomena, like a gesture that happens. And then you do usually some pre-processing into features, pass it to the model, and then you get your output class in this case. So each window is then the actual thing that we're predicting on, it's the input to the model as independent instances. Just some tips on the sensor data readout. It's generally good practice to use the embedded storage in these accelerometers. Kind of let it fill its buffer there, and then you read out that all the time because you get perfect sampling. But it's actually quite important in MicroPython because we do have a garbage collector. So if you would be trying to read 100, like every 10 milliseconds, so 100 hertz, you would occasionally be thrown into the garbage collector, and you might miss that 100 millisecond window, so you get some jitter. But even in C, it would be best practice to use the first in, first out buffer that are in these devices. And it's quite doable. So we wait for there's to be enough data on the device. So now we're talking about the sensor that is attached to our microcontroller buffer there. And then when there is enough, we just read a suitable amount. And we do this windowing that I showed in the previous one. And we decode the data. We run it through our preprocessor. I'll show an example of that, I think. And then we pass those features to the model, and we get our output. And then we would do something with this, like blink a LED, or send a Bluetooth message that goes to your phone, or trigger something on your smart home from Wi-Fi, or whatever you want. So this feature engineering, the best, it's, as always, you must make sure that it's compatible when you're doing machine learning. And now you have two worlds, the device world and your training world, to make sure that they have compatible preprocessing. So the best is to write the preprocessor that is compatible with MicroPython, and then reuse the same code in Python, and you know that it's compatible. And there's like, if you use the MicroPython specific things, like it has a assembler that is accessible in Python, so like Numba, basically, Numba-JIT. That will run on device. It's super cool because that allows you to get like close to C speed in pure Python on the device. You have to call MicroPython as a program that runs on your computer. Yeah, so the training of the model you do in the standard way. Here is the example how to do the pre-processing features, got them on a batch. And then we create a standard random forest classifier from scikit-learn. However, the defaults for scikit-learn are quite large models, 100 trees or something like that, and infinite depth. So that can easily become too large. So you probably want to start something closer to this, not to blow up all the space. And yeah, so this is very familiar, and you do your evaluation and so on. So this was the results on that very simple task, but near perfect on the test. Yeah, and then once you have that model with standard Python process, then you can export this, and this is where emlearn comes into place, because we do a little bit of optimization, and then we have a CSV kind of format that you export. So these are it's random tree, it's like the weights of your model, right? That can be loaded. So, and then on the device side, you need to copy the CSV to the device. And on the device side, you create a model. You have to specify manually the capacity, like how big could this model potentially be. And then you can load the model or load the weights into that model. So a couple of lines on each side. That's all you need. And then that will be a running system, which will classify gestures in this case. And this would basically be the same exact approach if you have other type of accelerometer type data, for example, like fitness tracking, a number of repetitions, or just a classic smartphone functionality or smartwatch functionality of running versus jogging versus biking versus sleeping and so on. So this is the entire process. So to summarize the talk, machine learning on microcontrollers, so-called TinyML, it's a good keyword to search if you're looking for more information, is useful to extract information from sensor data, accelerometer, images, microphone, etc. Radar is getting very cheap, LiDAR as well. LiDAR is a lot of data, but doable as well. And current microcontrollers can actually run MicroPython in Python, familiar environment to you, which is super cool, I think. And emlearn MicroPython is a machine learning library, which is designed to be easy to use and have the C performance accessible package. So that's all I had. Thank you.
All right, thank you, Jon, for your presentation. Maybe one question. Does emlearn MicroPython provide access to microcontroller hardware-specific function, such as timer interrupts, because they are not provided with Python?
Yeah, that's a great question. Yeah, there's a machine module and a couple of other modules which will give you access to basically all the microcontroller-specific functionality from Python. So yeah, everything that you would not necessarily everything, but the goal is to have everything accessible. Maybe there's on most ports 90% of the stuff is accessible from Python.
All right, thank you. So just a reminder, for any more questions, follow Jon, and maybe you are a lucky one to get one of these microcontrollers. And for now, please give another round of applause, please.